using phase changes in refrigerants for power generation with small temperature differences. If you have ever noticed the pressure gauge on a gas cylinder, you might find that the pressure is higher during the day and lower at night. This indicates that the day-night temperature difference can cause a gas pressure difference, and this pressure difference might be used for power generation. As shown in the diagram, Figure 1a is a high-pressure chamber on the ground containing liquid gas, designed to exchange heat with the atmosphere. B is a high-pressure chamber underground, also containing liquid gas, designed to exchange heat with the surrounding environment, such as groundwater. C is a generator that uses the pressure difference between the two chambers to generate electricity. To operate with very small pressure differences, the air pressure liquid flow generator introduced in a previous video might be considered. Since the underground temperature is almost constant, at noon, when the atmospheric temperature is at its highest, the temperature in chamber A will be higher than in chamber B. As a result, the gas in chamber A evaporates into vapor, increasing pressure, which drives the generator and condenses in chamber B. At around midnight, when the atmospheric temperature is at its lowest, the temperature in chamber A will be lower than in chamber B. As a result, the gas in chamber A condenses into liquid, reducing the pressure, while the gas in chamber B evaporates, drives the generator, and condenses back in chamber A. This way, electricity can be generated using the day-night temperature difference. Next, let us calculate how much electricity can be generated. For safety considerations, neopentane, which is less likely to explode, has lower vapor pressure, and is less prone to leakage, is chosen as the medium. According to the Clausius-Clapeyron equation, as shown in equation 1, dP over dt equals L over T delta V, where P is the pressure, P is the absolute temperature, is the molar heat of evaporation of the heat transfer medium, and delta V is the volume change. The latent heat of vaporization of neopentane is known as L equals 22.5 kilojoules per mole equals 22,500 joules per mole, and its boiling point is T equals 283 Kelvin. Assuming the liquid volume is negligible, the volume change can be expressed using equation 2. Delta V is approximately equal to V sub gas equals RT divided by P, equation 2, where R is the gas constant, equal to 8.314 joules per mole per Kelvin. Since the boiling point of neopentane at 1 atmosphere is 9.5 degrees Celsius, approximately 283 Kelvin, this temperature range is chosen for calculation. At this temperature, the pressure P is approximately 101325 pascals. Substituting these values into equation 2, the molar volume change is approximately 0.0232 cubic meters. Substituting this result into equation 1, the rate of pressure change with temperature for neopentane at 283 Kelvin is approximately 3,427 Pascal per Kelvin. Assuming the generator operates when there is a 10 degrees Celsius temperature difference, the pressure difference across the generator is approximately 34,270 Pascal, or about 0.34 atmosphere. Assume the volume of liquid neopentane is 20 liters, approximately the size of a household gas cylinder. Since the density of liquid neopentane is ρ equals 0.627 grams per cubic centimeter, and the volume V equals 20 liters equals 20,000 cubic centimeters, the mass of the liquid is 12,540 grams. The molecular weight of neopentane is 72.15 grams per mole, giving a total amount of 12,540 divided by 72.15 equals 173.804 moles. The heat of vaporization of neopentane at 1 atmosphere of 9.5 degrees Celsius is 22,500 joules per mole. The heat required to fully vaporize the liquid is 173.80. 4 times 22,500 equals 3,910.6 kilojoules. At 1 atmosphere, using equation 2, the vaporized volume is approximately 173.80, 4 times 8.314 times 283 divided by 101,325 equals 4.0359 cubic meters. With a pressure difference of 34,270 pascals, the mechanical energy generated is given by equation 3. E sub mech equals delta P times V sub gas. The mechanical energy is 4.0359 times 34,270 equals 138.310 kilojoules. Assuming the generator efficiency is 90%, the generated electrical energy is E sub elec equals 138.310 times 0.9 equals 124.480 kilojoules. If electricity is generated once at noon and once at midnight, the total daily energy produced is approximately 248.96 kilojoules. The thermal to electric conversion efficiency is 124.480 divided by 3,910.6 equals 3.1831%, approaching the theoretical limit of 10 divided by 283 equals 3.534%. If the risk of explosion and fire from neopentane is a concern, a high boiling refrigerant like 1-chloro-3,3,3-trifluoropropene, E, can be used instead. For the same 20-liter liquid volume, using similar calculations, approximately 339.6 kilojoules of electricity can be generated daily at a temperature difference near 18.5 degrees Celsius. The generated electricity is not substantial due to the small day-night temperature difference. When a stable heat source is available, the structure can be modified as shown in Figure 2, where Chamber A is placed on the high-temperature side and Chamber B on the low-temperature side. The heat transfer medium in Chamber A can use a liquid-to-liquid design, with hot water flowing directly through the lower end of Chamber A for efficient heat exchange. The main difference from the structure in Figure 1 is the addition of a pump, shown as D in the diagram. This pump only needs to return liquid from Chamber B to Chamber A at about 1/200th of the generator gas volume to maintain continuous operation. Pump D can be powered by generator C, and due to the small volume ratio, almost no energy is lost in returning the liquid. With this design, combined with the previously introduced air pressure liquid flow generator, electricity can be generated continuously even with small temperature differences. We can apply a similar concept to power generation using day-night temperature differences. As shown in the third diagram, Figure 3 on the left, pump D is modified to be bidirectional, and is also driven by generator C, but the liquid flow is opposite to the gas flow. During the daytime, when the temperature of Chamber A on the surface is higher than that of Chamber B underground, gas flows through generator C from Chamber A to Chamber B. Meanwhile, the liquid heat transfer medium is pumped back from Chamber B to Chamber A through pump D to replenish the heat transfer medium consumed in Chamber A, as shown by the red arrows in the diagram. At night, the flow directions are reversed, as shown by the blue arrows in the diagram. This ensures that the power generation is not limited by the depletion of the heat transfer medium.